Welcome back, student. The previous lecture video we discussed on already that what is VCR cycle, what is refrigerant, and what are the desirable properties of refrigerant, what is the designation of how do you define or how do you designate the refrigerant, okay, and what are the different types of refrigerant that are basically used in our RSC unit. So as you know that VCR cycle, okay, so VCR cycle basically vapor compression refrigeration cycle. And as you know that refrigeration cycle, basically there are two types of refrigeration cycle. The one is vapor compression refrigeration cycle, another is vapor absorption refrigeration cycle. In the vapor compression refrigeration cycle, the vapor refrigerant is compressed and produce actually refrigerant effect. Okay, and in case of VRR cycle, mean vapor absorption refrigeration system, the vapor refrigerant is absorbed and heated and producing the refrigerant effect. So this is the basic difference between VCR and VRR. Instead of that, in case of VCR cycle, the mechanical energy basically used to transform or to change the vapor refrigerant from one state to another state or to change the thermodynamical properties. Okay, but in case of VRR cycle, only chemical energy or heat energy basically produced for VRR cycle. Okay, now as you know that VRR cycle means vapor absorption refrigeration cycle is basically, the name suggests, the refrigerant is absorbed and heated and producing refrigerant effect. So that's all. Now, but before going to the elaborately in this topic, the vapor absorption refrigerant, it's basically the oldest method of producing refrigerant effect. This is the oldest method because this is the first producing refrigerant effect method was that VRR cycle, and it is discovered by Michael Faraday. Okay, Michael Faraday. Now, in the VRR cycle, vapor absorption refrigeration cycle, the refrigerant which is basically used, that is ammonia, and absorber used as a water. So that's why it is sometimes also called aqua ammonia solution or aqua ammonia refrigerant system or VRR system. Now, as we discussed that it is basically uses the heat energy to transform or to change the condition of refrigerant throughout the refrigerant process. So all of the process are same, but just the difference is with VCR to VRR is that here VCR means in the compressor is not here. Okay, so that's why compressor is not here. So in replace of compressors, the compressor basically replaced by absorber, pump, liquid pump. This is a generator and this is the pressure reducing valve. So compressor basically replaced by absorber, liquid pump, generator and pressure reducing valve. So these four things is replaced by compressor in VCR with VCR. Okay. Otherwise, the component is condenser, receiver, expansion valve or evaporator. Both are used in case of a VCR cycle also. Now, what happens in VCR cycle is that so in the evaporator, suppose this is the evaporator. In the evaporator, as you know, the main function of evaporator to absorb heat from the system so that it maintains low temperatures. Okay, so evaporator, so obviously after absorb heat from the system, the refrigerant is transformed. His phase means it's transformed into low pressure ammonia vapor, means low pressure liquid ammonia to transform into low pressure ammonia vapor. So because ammonia is used as a refrigerant, that's why refrigerant ammonia is transformed its phase, that's liquid ammonia to liquid vapor. As you know that in the VCR cycle we already discussed there are two pressure side, low pressure side and high pressure side. Condenser was the high pressure side and evaporator was the low pressure side. So that's why from the evaporator that comes out from the evaporator, that is basically low pressure ammonia vapor. Okay, so low pressure ammonia vapor comes out from the evaporator and it enters into the absorber. When the absorber, the absorbent agent actually that is basically used, that is basically water. Okay, now water absorb low pressure ammonia vapor. Now why water is used? Because water has capability, because water is the maximum capability to absorb ammonia vapor. to absorb maximum capability. So that's why water is used as a absorber. Now water is used when it absorbs continuously in manner from the evaporator. So they will increase some temperature. Okay, they will increase some temperature within the absorber. It happens, but as you know that if the temperature is increased in the absorber, the capacity of absorbent, the capacity of absorb of liquid ammonia, low pressure ammonia vapor is reduces. Okay, so that's why some cooling devices or some cooling agent are used in case in the absorber, so that temperature is kept minimum, so that the capacity of absorption actually increases. Okay, so there are some cooling devices or cooling agent are used in case of in the evaporator, in the absorber, so that maximum amount of ammonia vapor is absorbed by the absorber. Okay, so when the maximum amount of ammonia vapor is absorbed in the absorber, so they will form a strong solution. Okay, so this strong solution comes out after all from the absorber. Now it goes to the generator by through liquid pump. Because this is a low pressure site, so you have to increase the pressure so that it can reach in the generator. So by through liquid pump, the strong solution goes to the generator. In the generator, some cooling, some heating coil are there. So this is a heating coil. So it is a heating coil. So heating coil or heating produced. This is a heating coil. Now heating basically produced or heating is produced by basically steam or gas, like any other external source, by external source. So after heating, the ammonia vapor is driven off, and the rest that is the high pressure. So that's why the high pressure ammonia vapor is driven up and goes to the condenser. But the remaining liquid ammonia vapor, which is remaining part of that particular from the solution, that will be back to the absorber. This is called basically weak solution, that back to the absorber through pressure reducing valve. Because it is a high pressure zone, you have to go beyond low pressure zone. Low means low pressure zone, so you have to reduce. So you have to use some pressure reducing valve so that it can transform from high pressure side to low pressure side. That's why it is used as a pressure reducing valve here. Now high pressure ammonia vapor goes to the condenser. As you know, so in the condenser, some cooling devices, some cooling water is passes through that. So after the high pressure ammonia vapor is transformed into high pressure liquid ammonia after condenser. So this is the high pressure liquid ammonia. This is the receiver. This is the receive. The liquid ammonia is the receive here, and after that the liquid ammonia by expansion valve. High pressure liquid ammonia is transformed or it changed into low pressure ammonia vapor, low pressure liquid ammonia refrigerant. Okay, and this low pressure liquid refrigerant is basically in the evaporator. So in this way, total cycle is working. In the working cycle complete is here. So this is a vapor absorption refrigeration cycle. So which is basically oldest cycle, but it is basically used also industrial as well as some domestic applications. And but it has due to the reduces of compressor here, because the compressor is replaced here. This is the most important point. And one more point is that here it is no mechanical energy are used, because there is only used that is basically heat energy or chemical energy, because of to interchange or to change the condition of refrigerant. Okay, so this is a VRR cycle. Okay. So as far we know that what is VCR cycle and what is VRR cycle. Now VCR cycle is vapor compression refrigeration system, or cycle you can say that, or vapor absorption refrigeration system, VRR system. Okay, so today we'll discuss on comparison between VRS and VCRS, means vapor compression refrigeration system and vapor absorption refrigeration system. Now first of all, the first point is that for VRR cycle is that only moving part, in case of VR, only moving part is pump. It is basically subjected to little wear due to presence of small motor in pump. In case of VCR, that it is more wear due to moving parts of the presence in the compressor. So as you know that in case of VR cycle, one liquid pump, because compressor is replaced by a liquid pump, absorber, liquid pump, generator, and pressure reducing valve. So as we know that there are some pump are there. So in pump there are some small motor are there. Due to the usage of small motor, there are possibility to chances actually to produce wear. So that amount of wear in case of VR cycle is less because there is only moving part, that is pump. Okay, that is basically moving part is basically pump. In a pump, that is basically moving part that which produce actually little wear, that is a motor. Okay, so that's why it produce little wear in case of VR cycle, VR system. And in case of VCR system, it is it produce actually more wear due to the presence of more moving parts in compressor, because in compressor there are so many moving parts are there. So that's why that produces actually more moving parts, and that produces more wear. Now second point is that it uses heat energy, or it sometimes also called it uses low energy, because the low energy or heat energy in case of VR cycle that produce actually that uses to transfer the state, or to transfer the condition of the refrigerant when the refrigerant flows through the refrigeration cycle. So it uses the heat energy or low energy to transfer, or to alternate the condition, of refrigerant when the refrigerant flows through the refrigerant cycle. So it uses the heat energy only, but in case of VCRs, it uses mechanical energy, which is basically high gate energy, to transfer or to change the condition of vapor refrigerant. Okay, the third point is that VR cycle basically used when the electric power is difficult to obtain, because there is no as such electric power is required, but it can be used as solar power also used to produce the refrigerant effect, to heating the coil. So all these things can be adjustable by using the solar power plant or solar power or any such type of devices. So but it is not required that electrical parts, so electrical power is mandatory. It's not for this VR cycle. But in case of VCR cycle, electrical power is required to move, or to control, or to drive the compressors. Otherwise, the VCR cycle will not be completed. Fourth point is it's very expensive, because there are some solar devices or some solar plant like this type of arrangement should be there, because it is uses only heat energy, or it is uses only some gases, some steam energies only actually uses to transfer the condition of vapor refrigerant, or to produce the refrigerant effect. So very expensive, but in case of VCRs, it is less expensive. Similarly, the COP means coefficient of performance. As you know that coefficient of performance is net refrigerant effect divided by net work done. So in case of VR cycle, or in case of VR system, the COP is less, but in case of VCR, it is the COP is more. And the leakage problem is less in VR system, because in VR system that working condition basically they works basically in low pressure conditions, means compared to the VCR, because in case of VCR they are produced high pressure region. So that's why the chances of leakage of refrigerant very high in amount, high percentage. So leakage problem is more in case of VCR, but leakage problem is less due to the low pressure in the working system. And next, COP and capacity very sensitive to evaporate temperature. COP and capacity, as you know, that COP is a main tool, like you can say that indicate the performance capacity of any refrigerant system. That COP and capacity is basically very sensitive to evaporative temperature, and not very sensitive, but in case of VCRs. And these are partial load performance is not affected. Partial load is not very affected in case of VR, but in case of VCR, partial load performance is very poor. Okay, so these are the difference between VRs and VCRs, very important. Okay. Now let's take a numerical on VCR cycle. Now the numerical is that a VCR refrigerator works between the pressure limit of 60 bar and 20 bar. So the pressure limit is given in your numerical, that a vapor compression refrigeration cycle that works within a particular pressure limit, that is within 60 bar and 20 bar. So the pressure is 60 bar. As you know that in a vapor VCR system there are two sides. One is high pressure side, another low pressure side. So in case of VCR The high pressure side basically the condenser side, and the low pressure side basically evaporator side. So the 60 bar and 20 bar, in between 60 bar and 20 bar, the 60 bar pressure means that indicate the pressure of the condenser, means the condenser pressure, and 20 bar indicates the evaporator pressure. Okay, now as you know that PV and PV, TS and HS plot for a VCR cycle or VCR systems. Then the working fluid is just dry. So working fluid means refrigerant, because the working fluid which flows through a particular refrigeration cycle, that is called refrigerant. Now refrigerant is just dry at the end of compressions. So after compression process, the refrigerant conditions, the condition of the refrigerant is basically dry, not wet or superheated. So it's a dry in conditions. Okay, and there is no undercooling takes place before the expansion valve. Now you have to calculate or determine the COP. First, coefficient of performance. Number 2, capacity of refrigerant if the fluid flow is at the rate of 5 kg per minute. So fluid flow is at the rate of 5 kg per minute means that the refrigerant flow rate, that is 5 kg per minute. Okay. First of all, you have to calculate the COP, means coefficient of performance, and capacity of refrigerator. Now, so these are the table. So this table in your numerical is given in numerical that the corresponding properties of actually the refrigerant properties for corresponding pressure and temperature limit, that is for enthalpy and entropy is given. Now for pressure, the value is here: pressure, saturation temperature, enthalpy, entropy. Okay. Now pressure is 60 bar, 20 bar, saturation temperature in Kelvin in 295 in 261. It is in bar. Okay, pressure in bar. So it is given in numerical. Pressure is your bar. So pressure in your bar, that is 60 bar, 25 bar. Saturation temperature is 295 Kelvin, is 261 Kelvin. Okay, enthalpy also liquid and vapor. So enthalpy liquid is basically for 151.96, 56.32. For enthalpy vapor enthalpy, that is 293.29 for corresponding 60 bar, and enthalpy is 322.58 corresponding pressure 25. Now similarly the entropy of liquid and vapor is given. Now as you see in your chart, so these are the value I've given for the particular properties of refrigerant. Okay, means particular thermodynamic properties of refrigerant. Okay, now this is a TS and pH diagram plot, actually temperature, entropy, and pressure enthalpy plot. Okay, and as you know that in VCR system or VCR cycle, there are 4 processes there. First of all, in compressor, the compression process takes place is from process 1 to 2. In case of process 2 to 3, there's a condenser, there's a constant pressure cooling process. Okay, and process 3 to 4 is that there are expansion valve are there, because to expand means to decrease the pressure. Okay, means to increase the pressure. Okay, so after all, if the pressure limit is very much high, you have to reduce the pressure from P2 to P1. Okay, by means of expansion valve or capillary tube or throttling devices. It is used in process in 3 to 4, and in case of 4 to 1, their evaporator are there. So if you plot these things in a particular thermodynamic plane, means PV, TS, HS, and PS diagram, it will be look like this one. So as you know that from TS diagram, this plot seems like that process 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Similarly, corresponding this is the TS diagram of VCR plant. So corresponding TS plot, this also a PS diagram. Similar processes occurs in case of also VCR system. Okay. Now, so what are the value are given? Just write down first. So for pressure 60 bar, that means the pressure is high pressure side. That means in condenser pressure. That's why if P2 is equal to P3 is equal to 60 bar. Okay. And the corresponding P2, if P2 is equal to P3 is equal to 60 bar, the corresponding temperature means T2 is equal to T3 is equal to 60 bar, mean 295 Kelvin. So P2 is equal to P3 is equal to 60 bar, T2 is equal to T3 is equal to 295 Kelvin. And pressure at 25 bar means at the lower pressure side, that is evaporator pressure side, and process 4 to 1, as you know that the evaporator process takes place, means evaporation takes place or refrigerant. So process 4 to 1, that means P1 is equal to P4 because of This is a constant pressure process. So TH diagram is a constant pressure process. That's why P1 is equal to P4. That is equal to 25 bar, right? So corresponding temperature will be T1 and T4. So T1 is equal to T4. So that means basically TH diagram, that also constant temperature line. So T1 is equal to T4 is equal to 61 Kelvin. So in the remaining part of the chart, actually, what are the value are given? We will see that. First of all, the corresponding, this one means corresponding pressure 60 bar means corresponding condenser pressure, the value of liquid enthalpy and vapor enthalpy is given. So liquid enthalpy 151.61. So 151.96. Sorry, 151.96. That means this one. So as this P2 is equal to P3 is equal to this line. Okay, P2 is equal to P3 is equal to this line. This corresponding line, as you know, this is a saturated liquid line, this is the saturated vapor line, and this value is for liquid enthalpy. So this is the saturated liquid line. So the enthalpy of this particular point is your liquid enthalpy, that is 151.96. So that is your HF3, right? Now if it is HF3, this is a pH diagram and this is a perpendicular line. Okay, see, a perpendicular to HF, that means HF3 is equal to H4. So HF3 is equal to H4 is equal to 151.96 kilojoule per kg, right? And HF1. So HF1, that means for corresponding evaporator pressure, the liquid enthalpy is 56.32. Suppose this is your pressure limit P2 and suppose this is your pressure limit P1. So that means the enthalpy is given. Liquid enthalpy given the particular corresponding state of 1. That means HF1 is equal to 56.32 kilojoule per kg, right? And Hg2, right? Hg2. So this is the line. This is the plot diagram. This is the vapor enthalpy. Vapor enthalpy at state 2. That means 293.29. So this is the point. This is the 293.2. This is the 293.29 vapor enthalpy. Okay, that is basically Hg2. Okay, that is equal to Hg2. That is nothing but H2, right? And for Hg1 is basically the corresponding pressure level, that is 1. Suppose this is basically one state, this is 2 state. For corresponding state 1 means evaporator pressure, the vapor means Hg1 that is given here 322. So Hg1 322 is given. Similarly SF2, SF1, Hg2, H2, and these are the value are given. Now as you know that process 1 to 2 is from TS diagram. As you know, the reversible adiabatic process, that means it is, if it is a reversible adiabatic process, that means the entropy is constant. So you have to calculate, and this one point is basically in a wet in compressions. The compression process takes place, means at the starting of the compression is basically wet in conditions. So when it is wet in condition, that means there are some liquid refrigerant are present when the refrigerant enters into the particular compressor device. So obviously one process, there are some dryness fraction are there. So first of all you have to calculate the dryness fraction factor. That's why, as you know, that S1 is equal to, from the properties of pure substance, that S1 is equal to SF1 plus X1 into SFG1. So put this value SF1 SG1. So S1 will be this one. S1 will be this expression. Okay, and S2 basically nothing but this is Hg2. Hg2 means entropy at vapor state, that is 1.0332, right? So that is corresponding this one, this value, and 1 and 2 is the constant entropy line. So constant means S1 is equal to S2. So that becomes this one is equal to this one. So that becomes X1 is equal to 0.791. Now, as you know that COP means coefficient of performance, and coefficient of performance basically is a ratio between the desired effect, desired refrigerant effect divided by net work done. Now desired refrigerant effect, that means your Q2 divided by net work done, that is W. Now already discussed that Q2 you also write down as, because net refrigerant effect Q2 is equal to H1 minus H4, right? And net work done, that is equal to H2 minus H1. So put these values, H1, HF3 means HF4 also, and H2 minus H1 means H2, H1 and HF3. These three enthalpy values you have to require to calculate the COP. Now, this HF3 value is nothing but, that is HF3, this is nothing but HF4. So value is given, right? H2 is nothing but Hg2. So Hg2 is equal to H2. These two values given, but H1, because one state is basically in drying condition, means wet in condition. Wet compression process takes place at the starting of the compressor. Now, if it is one is your wet compression region, mean liquid vapor dome zone. So when you calculate the enthalpy, so there are some properties of liquid as well as vapor properties are there, enthalpy properties are there. So that will be H1 will be HF1 plus X1. This is a Dynamis fraction factor into HFG1. So put all these values, X1, HF1, HG1 as well as HF1. Then you can calculate H1. So put these values H1 there, and you can calculate COP. COP will be 4.36. So this is the coefficient of performance for a particular refrigerator plant or VCR refrigerator. Okay. And the second part of the numerical, that you have to calculate the capacity of refrigerator. Okay. So in the second part of the numerical, you will calculate the capacity of refrigerator. Now, if the fluid is flow at the rate of 5 kg per minute, so fluid flow rate is given, that is 5 kg per minute. Now you will calculate the capacity of refrigerator. Now, what is the amount of heat extracted? Means amount of heat extracted is defined. Actually, the amount of refrigerating effect. That is nothing but heat extracted per kg of refrigerant. Means in case of per kg of refrigerant, what amount of heat extracted is, that is the basically capability of particular capacity of refrigerator. And for per kg of refrigerant, that is nothing but H1 minus HF3, because Q2 is your particular desired effect, okay, or desired effect or heat extracted, you can say that, for a particular system. So for the flow of per kg rate of, means per kg of refrigerant, the amount will be H1 minus HF3. Now value of H1 already you have calculated. So put this value 266.93, and HF3 is 151.96. That is nothing but your HF4. Sorry, H4, not HF4. That is HF3 is equal to H4. Now put these two values here, H1 and HF3. You can get that heat extracted per kg of refrigerant. That will be 114.97 kilojoule per kg. Now, since the flow rate is 5 kg per minute, means in 1 minute the refrigerant flows to a particular refrigeration cycle, that is 5 kg. Now, if the fluid flow is rate, means the refrigerant flow rate is 5 kg per minute, and for per kg of refrigerant the heat extracted is 114.97 kilojoule per kg. So for the 5 kg it will be multiplied with that. So net total heat extracted will be 5 into that one. So 114.97 will be 574.85 kilojoule per minute. So this is the total amount of heat extracted for a particular refrigerant when the refrigerant flow rate is 5 kg per minute. Right. Now we have to calculate the capacity of refrigerator. As we know that capacity of refrigerator is basically defined or designated by ton of refrigerations. And 1 ton of refrigeration is nothing but 210 kilojoule per minute. You know that 1 ton of refrigeration, that is equal to 210 kilojoule per minute or 3.5 kilojoule per second. So both are same, but if you calculate the ton of refrigeration and total heat extracted is in your kilojoule per minute, so capacity of refrigerator will be 574.94 divided by 210, and that will be 2.74 ton of refrigeration. So this is the capacity of refrigerator. Okay. So okay, thank you very much for listening and watching me. And in the next lecture video, we'll discuss about the properties of dry and moisture air and psychometric chart, psychometric processes. So all these things will be discussed in the next lecture video. Okay, thank you very much for listening and watching me, and goodbye.